Hey crew, so I learned about the atmosphere here, and I got an old review I'd usually do with the kids in the class, so I'm going to do it instead with you here on the YouTubes, and we'll see how it goes. So, if you would, excuse me, follow along, and let's see how this goes. Okay, we'll start with this. We'll start with taking a deep breath. And breathe out. When you do that, I have one main question for you, which is, what's the main chemical you're breathing in? What are you mainly breathing in? Most kids will start by saying oxygen, and that would make sense because that's normally what people tell you you're breathing in. However, in the case of the atmosphere, that's not what you're breathing in. 78% of our atmosphere is actually nitrogen. And so nitrogen, for example, is what they fill your chip bags with to keep them from going stale, because oxygen only can go stale. So nitrogen is everywhere, and it's a very important chemical for plants and such. But for right now, and also for animals for making proteins. But the main thing I want you to realize is that when you do breathe in, you're mainly breathing in nitrogen. Now, 20% of what you do breathe in is oxygen. And there's which is good for you. And then, of course, there's 1% that's argon, which is a noble gas and doesn't really do anything. But the point is, if you remember our song, mainly nitrogen and oxygen, the one we need is only 20%. Most of the atmosphere is 78% oxygen, or 78% nitrogen and 20% oxygen. And that's all the way up, all the way through the atmosphere. It's all the same ratio here. Somewhere around anywhere from 70 to 80% nitrogen and around 20% oxygen. And that'll be no matter whether it's the thermosphere, the mesosphere, the stratosphere, all that will be the same. It's just the higher you go up, the more the particles tend to spread out. And if we look through here, we'll see there are more other kinds of chemicals that you'll learn about in the 8th grade. But for right now, we have carbon dioxide here. That's the really famous one you'll see. That's only 0.036%. And 0.036% is not a whole lot. At least people don't think it's that big. And so because they don't think it's that big, they don't think it's that big a deal. The problem is you're talking about, more than trillions of particles. The number of particles in the atmosphere is insane. And so just 0.04% of something with that many atoms is a lot of atoms. And these things mess with global warming, and we'll talk about that more as we go. But only 0.04% of the atmosphere is carbon dioxide, and it causes some big effects. Let's start moving on through here. Okay, so looking at this some more. Gases that allow light from the sun through but do not allow heat back out, those are your global warming or greenhouse gases. Name a few of these greenhouse gases. Well, you got CO2, you have CH4 or methane, you have NO2, which is a nitrite, and or any of the nitrates. But also you have water. H2O is a greenhouse gas. People don't really realize that. UV radiation can cause skin cancer. The ozone layer protects us from UV rays, and that's, I'm just going to skip all this because we don't have too much going on, but there is one thing I want to stress, which is this: cause and effect. What's the cause? What's the effect? So the cause of global warming is excess CO2, CH4, and those other greenhouse gases. CFCs, or chlorofluorocarbons, cause the hole in the ozone layer, which we'll talk about more as we go. Okay, so greenhouse gases. On Earth, we have just the right amount of warm. It's not too hot or too cold. As the sun's light comes in, the Earth's atmosphere traps the heat, so light comes in, heat gets trapped, and it keeps the Earth nice and warm. So when you're on the backside of the Earth during the nighttime, it's not freezing. On the moon, which has no atmosphere and therefore no greenhouse gases, it gets ridiculously, like in the super 100 negatives type of degrees. So it's unlivable on the backside of the moon. That's why we only are ever on the day side. So that's an important thing to note, is greenhouse gases are actually good to a certain extent, because they keep the whole planet warm, not too hot, not too cold, as long as, again, there's not too many of them. Now, moving on through here, what else do we have? What's the order of the layers of the atmosphere? Well, we know that's the TSMT. TSMT is the order. All right, so you have the troposphere, stratosphere, mesosphere, and thermosphere. The layer of the atmosphere with ozone, that's our stratosphere. The coldest layer of the atmosphere, that's going to be the mesosphere. The layer of the atmosphere where meteors burn up, that's also the mesosphere. The hottest layer that absorbs all those X-rays and gamma rays, that's the thermosphere. That's the area that helps make the aurora borealis, because they're absorbing all that high intense radiation from the sun. And the layer where all our weather occurs, that's the troposphere, and that's a big one. All our weather occurs in the troposphere because the troposphere has 99% of our water. You can't have weather without water. Convection, conduction, and radiation. So these are pretty simple concepts. Conduction needs things to touch, and you see right here, the thermometer's touching the water and the sand. Over here, we have convection. That's where either liquids or gases go up and go down. We can see the cycling here of the air with our sea breeze. All right, and hot things go up, cold things go down. That's our idea of conduction. And simply radiation is what comes from the sun. Radiation from the sun. It can travel through space, and that's kind of the key thing, in all directions. And convection cycles the air. So if we look here, a very important little experiment, if you remember, where we have the dirt and the water, and if you heat both of them up at the same time, you're going to notice that the water is going to heat up slower. The sand is going to heat up faster. That's why the sand gets so hot on the beach. It's a conductor. It gets so hot on the beach during the day. However, this is also why at night the sand is super cold, because not only is sand a conductor, it gains heat well, it also loses heat well, so it gets super cold. The water will actually stay kind of or relatively warm. So what you'll notice here is that in the day, the water will be nice and cool compared to the land, and then in the evening, the water will be warm compared to the land, which creates the land breezes and sea breezes, which we've discussed. Okay, the big thing is this. Cold air is more dense and sinks. All right, that's key. More dense and it sinks. Dense things sink. You throw a rock into a pool, the rock's going to go down. Warm air is less dense and it rises, and that's why bad weather happens. Because as you heat up water, it evaporates, it gets less dense, it goes up high in the air, and then condenses and creates storms. And so if we're looking here, these are some of the big topics, especially for next year in 7th grade you're going to have to deal with, which are these Hadley cells. You won't talk about Hadley cells, but you will talk about biomes. And what you'll notice is every single biome along the equator is going to be a rainforest of some kind. And that's because the equator is where the hottest weather is. As a result, the water heats up a lot and it tends to rise. And rising water vapor condenses, forms clouds, and you get lots of rain. But as that water, right, the water vapor, I should say, starts to move out of the way, as new water vapor comes up, it pushes the old one out of the way, it condenses more and more and more over time until finally it's completely dry. All the rain finally goes away by the time you get over here, and it descends now. It's cool, it's dry because all the rain has rained out, and so when it descends here, this is where we get our deserts. You notice the deserts primarily at the 30 degrees latitude north and south. And that's because by the time it gets to these, it goes up, rains, 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 dry, 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 and fall. That's kind of how those Hadley cells work, and that's why we get the biomes that we have on the Earth. Now, Coriolis effect, I'm going to skip because at the end of the day, y'all don't really need to worry about that. That's a tough concept for college. So what are these? Well, here we have our cold front. Here we have our warm front. These cold fronts, you can see the arrows are pointing this direction, so it's going down to the right. The warm front here is pointing up to the left. All right? In terms of what weather we get, so if you look at a cold front, what you're going to get, I think I have some images here. Do I have some images here for you? I do not. Oliver. Okay, so let's take a look. Whenever you get a cold front, what happens is the cold blue air comes in, right? And as it comes in, it forces warm, moist air up. And this is happening during a cold front. And when you get a cold front, the real issue is you get thunderstorms, really nasty, bad thunderstorms. Because as it goes up, it reaches colder air up there and creates storm clouds, etc. And you get a really intense, short-lived, but a really intense thunderstorm during cold fronts when cold air comes in. Now, if we reverse it and say warm air is coming in, well, warm air, as we know, is less dense than cold air. So what it's going to do is it's going to push the cold air out of the way, but it's also going to go over top. And as it goes up, again, it's running into more cold air. Let me put a warm front over here. So what you'll notice is as it goes up, you'll get these kind of like, I don't know, drizzly, miserable days. Not really thunderstorms, just lots of low-lying clouds, maybe some drizzle. It's just going to be a miserable, long, rainy day. Some people like those days. I find them to be kind of miserable because it's just constant rain all day. No thunderstorms, but just this. Okay, so cold fronts are required for thunderstorms. Warm fronts make long, rainy, drizzly days. Now, these are two really very important concepts you're going to need to know, especially for your quiz you're going to take later. So if we look at it, we need to know which one's low pressure and which one is high pressure. So if I'm looking at these, anything going up means it's less dense. And anything that's less dense is only less dense because it's warmer. So anything going up has to be warm. And if it's going up, we get this called a low pressure system. It's low pressure because this is the actual air in the atmosphere, which is normally pushing down on you. It's normally pushing down. But when it warms up too much, it starts to go up, so you feel less pressure on your head. Okay, so when the air is going up, we call this a low pressure system because you don't feel anything on your head. It feels low pressure to you. Okay? All right. Now, over here, we have a high pressure system. It's high pressure because the air is coming down. The only reason air can come down is because it's cold. That's why I'm coloring this blue and this one red. Low pressure means higher heat, right? And it rises. Over here, we have less heat. It's colder. It's more dense, and it falls. So we have a high pressure system because you're sitting down here, and all this air is falling on your head. Excuse me. And you can actually feel that pressure. And people note these changes in pressure when they know storms are coming, or if it's going to be good weather. Now, continuing here, you see again more of this. Again, air rising only because it's hot. That's why you see the red over here. Air descending because it's cold, high pressure. The nice thing about high pressure systems is it's very dry. As we talked about with Hadley cells, by the time the air gets really cold, it starts to fall. Okay, but when it's cold like that, it also doesn't have very much moisture in it because, again, it's cold. So it's dry air. So in these situations, you get perfectly beautiful, sunny, clear skies. In fact, if I take a peek out here, and you guys can see that sky, you might not notice any clouds. And that's because we're in the middle of a high-pressure system. There's not enough moisture up there in the atmosphere. All that cold air is descending down here. All right? And that's what you see on the screen. You got cold, dry air descending. Beautiful, sunny weather. Nothing but sunshine and sunlight all day. Okay? In fact, if you notice today, it's actually kind of chilly. Over here, we have a low-pressure system. Low-pressure systems, you have warm, moist air. That is lots of water vapor, H2O. And that starts going up. And when it does, it reaches the cooler air above and turns into storms. These low-pressure systems are where we get our terrible, awful thunderstorms. It's my best lightning bolt there for you. Sort of a... Is that a lightning? You get the idea. All right. Now, moving on over here. This is a really famous, important cloud. This is called a supercell. You should know what these create. So supercell thunderstorms are where you get an intense amount of low pressure. All right, you got this cold front coming in. Big temperature differential is important for tornadoes. So you have warm, moist air being flung up by all of the cold front coming in, and it creates this huge thunderstorm called a supercell. And that's what makes tornadoes. These supercells create tornadoes. Coming over here, you can see the cumulonimbus cloud. We should know that one. Cumulonimbus meaning white fluffy, but nimbus meaning storm. So we get this beautiful anvil here in the general direction. So again, updraft, low pressure system, which means lots of warm air. The cold air comes in and literally flings this warm air up. In fact, I should probably change these. Warm, moist air goes up and creates a terrible thunderstorm as the cold air comes in. And then you get those tornadoes start to form, which you can see here. Okay, lots of this rotation because of the convection currents going on inside those winds with the warm and cold air mixing. Hurricanes. This is very, very important. So in order for hurricanes to form, what do you need? You need warm water. That only works with warm water. In fact, it's got to be pretty much anything over 80 degrees. And if we know anything about 80 degrees, we should know that in the ocean, that's hard to get. So we only have a small chance of a hurricane, or small window of a hurricane season where the water is that warm. However, with global warming, we should understand that the higher the temperature goes up on the Earth, the higher the temperature goes up in the ocean. That means that 80 degrees Fahrenheit in the ocean happens more frequently. And when 80 degrees happens more frequently, that means we have a longer hurricane system. And so, hurricane season. And so we could end up potentially with more hurricanes because it's a longer season. But more likely, we're going to end up with stronger hurricanes. And you might have seen that over the past couple of years. We get the really strong, intense hurricanes because the water temperature is so warm. And when the warm water temperature, you get more evaporation. More evaporation, as you see, goes up here, makes bigger and bigger clouds, and therefore bigger and bigger storms. So hurricanes are dependent on evaporation. That's why when they go over land, they usually stop pretty quickly because there's no more water vapor feeding it. All right, it's a feeding frenzy. All that sunlight coming in right? From over here, all that sunlight coming in, heating up the water, water going up. That's what's causing our serious hurricanes. Ignore my shirtless son walking around in the background. So those are the major topics and everything you really need to know about them for the quiz, as far as I'm concerned. So if there's anything else that I could think of, I'll let you know. Otherwise, hopefully I'll see you guys tomorrow, and good luck on this quiz if you decide to take it. Love you all very much. Be safe, and have a great day.